My name is Jeff Strock. I'm a professor in the Department of Soil, Water, and Climate and at the Southwest Research and Outreach Center near Lamberton, Minnesota. Um, I've been asked to give a talk on bioreactors, wetlands, and other nitrogen mitigation practices. Mainly, we'll be looking at potential practices that could be implemented in ag landscapes to mitigate the potential negative impacts of nitrogen that might be exported from agricultural lands. I need to make notation of my co-author, Andre Ranavasan. Andre is a wonderful colleague of mine who has worked very closely with me on collecting this data, analyzing this data, and interpreting the data and helping to screen the presentation prior to today. I'm going to turn off my video and just continue with the presentation. So the issue that I've been asked to talk about is related to nitrogen, of course, and agricultural water quality. In this particular screenshot, you see a figure there in the middle that shows nitrogen load reductions on the x-axis and shows potential practices on the left axis. These data were derived and extracted from the Minnesota Nutrient Reduction Strategy document. So these were data that were reported in that document that I've simply extracted out and put in what I hope to be a nice visualization for people to be able to look at and kind of condensed everything down into one figure for nitrogen. So the dashed line in the middle represents the 45% reduction target that we have in terms of reducing nitrogen from our agricultural working lands. Now, you can see on the left side of the screen there the different types of practices. The brown ones really represent what I kind of collaboratively call or collectively call soil fertility management practices. The next group up, the blue and the orange group, represent structural and non-structural practices. So, for example, constructed wetlands, controlled drainage would be examples of some structural practices, whereas cover cropping, we would consider that to be a non-structural practice. The top group in green basically represent practices that really involve perennial vegetation on the landscape. And those include obviously pasture hay, energy crops, CRP, and those types of things. Now, when we look at this information, what we can see is that of the 14 practices that were provided in the Minnesota Nutrient Reduction Strategy document, more than 50% of them do not meet the 45% reduction target. So those bars don't reach that goal. Cover cropping, constructed wetlands of the structural and non-structural practices do, based on the data that I extracted, as well as these perennial vegetation practices. Now, when we think about these types of things, one of the things that we need to think about is would it be realistic and practical to convert all of our ag lands into perennial crops, CRP, or pasture hay ground? The answer would probably not. So we're going to have row crop cropping systems out there. So how are we going to deal with some of this nitrogen issue? So one of the things we could think about is that we need to implement those practices that do achieve the target. So for example, cover cropping or constructed wetlands. We know that these are not perfect systems. We know that in the northern part of the country where we live here in Minnesota, that getting cover crops established can be challenging. If we don't get them established well, they don't perform for the purpose that they were planted, if that is to scavenge nitrogen, for example. Constructed wetlands, on the other hand, might be a great practice in some settings, can help improve water quality, may have some other ecosystem services by providing vegetation and aesthetic kind of reasons for being able to look at those types of things. But we probably, as I said, aren't going to be looking at wholesale, conversion of all of our lands into, these perennial crops, for example. So another thing that we might need to think about is are there other strategies, other practices that we might be able to implement? And I'm going to share one of those today that isn't on the list in this presentation. And then finally, one of the ways that I think that is really important to think about this is to think about these practices as from an integrated standpoint. So in other words, none of these practices, whether it's a bioreactor, a perennial energy crop, a cover crop, they're not a silver bullet that is going to solve the nitrogen issue wholesale. What we really need to be thinking about is an integrated approach where we use a combination of these types of practices where they fit. We know that there are some limitations and there are some advantages and disadvantages, trade-offs, if you will, to all of these different types of things. But if we can think about implementing the best practices where they're appropriate on fields, on farms, and within watersheds, then we'll be able to make some headway in solving our nitrogen issue. So to put this in perspective, the research that I'm going to be sharing today is done in southwestern Minnesota, in the Cottonwood watershed in particular. And the location where it's happening is basically almost right in the center of the Cottonwood watershed. This is the sub-watershed outlined in red here in the right figure, where the Southwest Research and Outreach Center is located. And the lands that we're talking about that are part of this experiment are really in the center there of that picture. So right here in this area, and all the water that drains from our lands actually flows up to the Cottonwood River. And this upper picture here is an inset of the actual details of the site. So the details of that site represent a beyond the field in-stream ditch practice that we have. It also involves edge of field constructed wetlands. It involves edge of field bioreactors, and it involves some in-field cropping systems management, also on some drained land. Now, the area that we're looking at where these practices are all integrated in together in one landscape on our farm, basically treat about 300 acres worth of the drainage and surface runoff water that we have coming from that part of the research center. So I'll go into a little bit of detail on the source water. It's important to kind of understand the source waters that we're dealing with before we start talking about treating those source waters. This figure on the right is another viewpoint of the same site that I just showed you from that bird's eye view, for example. So here in the middle, we have our drainage ditch system, the experimental ditches right here. Here in the back, we have our constructed wetlands. Just below those, we have our bioreactors, and then our cropping system field is up here in the upper right-hand corner. Now, our source waters come from a couple of different areas. We've got a surface runoff collection area up here on this hill slope, and then one down here at the bottom of this slope. We also have subsurface drainage monitoring locations, one again coming off of the upslope area here, and then another one down here right at the head end of our ditch systems. So when we look at this data for surface runoff, we have data that we're displaying here from between 2017 and 2019. 2017 was a marginally wetter year than our long-term average. 2018 and 2019 were much wetter than our long-term average. And what you can derive from looking at this is that there's a lot of variability from year to year in our surface water runoff, nitrogen, nitrate, nitrogen concentrations, and also in our loads coming off of the landscape. Some of this in terms of some surface runoff can be the timing, the extent, and the volume of water that's moving across the landscape has a lot of influence on this. But you can see that as it got wetter from 2017 to 2018 to 2019, there was increasingly larger amounts of surface runoff discharge that we recorded. When we look at our annual subsurface drainage data from our site, again, we see that the progressively wetter years of 2018 and 2019, as a result, we saw considerably more subsurface drainage outflow in terms of volumes of water under those conditions compared to that slightly above average year of 2017. Again, our flow weighted nitrate concentrations are quite variable. They're in that 14 to 18 milligram per liter range. And we can see that as our flow rate goes up, so too does the nitrogen load. Now, it's really important to point out here that in most of the research that I've done over the years, say, for example, comparing free drainage and controlled drainage, that the results of those studies really dictate that the flow, the discharge volume of water from the system really dictates the load that we see coming out, because we don't really see a lot of changes in concentration. So focusing in here on some of the ditch research, again, this is a very focused in image of the site. So in the site, we have a treatment channel here on the right side, and on the left, we have a control channel. The illustration up here on the right shows what I mean by that. So the control channel has no management in it whatsoever. It's treated just as any normal ditch in the region would be, where water comes in and water flows out of the system. Our treatment channel, on the other hand, you can see on this little illustration that there's a little change in elevation here. The water's higher up to this point, and then there's a drop to another level. At that location, we have what we're calling a low-grade weir. So that's in this image. You can see this horizontal line. That's our low-grade weir. This inset image up on the top above that shows a more detailed picture of it. And this low-grade weir is only 12 inches tall. So we're not trying to manage a depth of water in a ditch, feet deep. We're only looking at a very small elevation change in terms of holding that water back, trying to step it up a little bit, if you will, so that we can increase the hydraulic residence time and have more interaction between the water and the sediments and the water and the vegetation that are in that particular ditch. So our annual discharge and nutrient reductions for our drainage ditch system are in two parts here. The top table basically shows the year-to-year values that we'll talk about briefly, and then we'll talk a bit about our 3-year means. So as I mentioned earlier, the long-term mean precipitation is about 27 inches of rainfall. In 2017, we had about 3 inches more than that. In 2018, we had actually almost 12 inches more than that. And in 2019, we had nearly 13 inches more rainfall over the course of the entire year. So when we start looking at this again, you can look at it from year to year that the discharge from each of the ditch channels was a bit variable. The nitrogen load reductions between the two were also variable, and the nitrogen concentrations were somewhat variable. Of note here, though, is that our treatment channel in every year was always lower in cumulative discharge compared to the control. So less water flowed out of the treatment channel compared to the control channel. We also look at our nitrogen load values, and the treatment always had less nitrate load coming out compared to the control. What's also very, very interesting is that our flow-weighted nitrate concentrations were also lower, particularly in 2017 and 2018 compared to 2019, where it tells us that there were some biological processes going on in the ditch channel that reduced our flow-weighted nitrate concentrations by almost half and more than half in those 2 years. So when we look at the 3-year averages, we can see that there's about a 50% reduction in cumulative discharge between the treatment that had the low-grade weir and the control that did not. We see a similar result in the nitrate nitrogen load, and we also see that flow-weighted nitrate concentration also being about half. So this particular site is at the outlet of our system, and cumulatively all of the other practices that we're going to talk about today end up flowing through the ditch at the end. And so this is the cumulative improvements in the water quality that we've got coming out of our system. The closer look at the data, when we look at the monthly ditch data in terms of nitrate loads that are coming out, the ditch control here is at the upper left corner, the ditch treatment is at the lower right corner. We're broken down by colors, so green is 2017, dark blue is 2018, and the lighter blue is 2019. What this data shows us is a couple of different things. In the ditch control, it tells us that April and May, we tend to have our highest nitrogen loads coming out of our drainage ditch. We also see a little bit of a spike in July and then another in September. And this occurred in part because of the very wet years of 2018 and 2019, when we had some very large events occur in July and another large precipitation event or series of events that occurred in September, which increased the loads coming out of the control during those years. When we switch over to looking at the treatment, we look at the fact that the maximum load is less than half of what was coming out of the control on a monthly basis. So in the control, we were up around 1,600 pounds. Here, we're less than 800 pounds. And in particular, we can see that most of that's coming out in April, May, June, and July, and then really drops off in August, September, October. Next, we'll look at some of our bioreactor research. This picture shows the bioreactor site. So we have 9 different bioreactors. There's 3 groups here. And the illustration on the right shows that bioreactors are composed of cubes or modular cubes that contain corn cobs and wood chips. For the most part, are the reactive parts of this system. During the 2 years of data that I'll be sharing today, 2018 and 2019, we also added a heat tape or a heat cable that was at the interface between the corn cobs and the wood chips. So it was right here in the middle between those two as one of our additional treatments. That heat cable was engineered to provide warmth or additional warming for the water, and it was powered by our mobile solar power generator here, which is a nice piece of equipment that was a number of years ago funded by the Minnesota corn growers. So a summary of our annual bioreactor data from 2018 and 2019 show basically 3 treatments. We have a control, which was just corn cobs and wood chips, an acetate treatment that was corn cobs, wood chips plus acetate, and then a third treatment, which was corn cobs, wood chips, and then acetate and heat. Now, the acetate is a treatment that we used as a supplemental carbon source. Now, even though our control bioreactor is supposed to produce dissolved carbon for the biological organisms that live in the bioreactor on the wood chips and on the corn cobs, one of our hypotheses is that the system was limited for carbon, that there wasn't enough carbon in the system that was available to help stimulate more nitrogen reductions from the bioreactors. So thus we added a supplemental carbon source by itself, and then the carbon source plus heat during these 2 years. So our data show us that we have some statistically significant differences for the acetate and the acetate plus heat treatments, which are statistically different than the control in the flow weighted nitrogen concentration and in their load. The data tell us that there is no difference between the acetate and the acetate plus heat treatments. Although they're numerically different, they're statistically not different. So this tells us that at least under the conditions that we were working in these 2 years, that it may not be advantageous to apply heat, that acetate may be just sufficient to be able to create our reduction that we're looking for. So this is the bioreactor monthly nitrate load reductions. Again, we have a similar color scheme here. So the control is a light green, dark blue is the acetate, and the acetate plus heat is the lighter blue color. Of course, 2018 is the upper left figure, and 2019 is the lower right figure. Now, a couple of things that we can see from this figure is that there's quite a bit of difference in terms of the behavior of the bioreactors in terms of nitrogen load and the treatments between 2018 and 2019. There's more load, higher loads coming out in 2018 compared to 2019. So the magnitude of the values for all of the treatments was higher in 2018 compared to 2019. The other thing that we see is that in general, on average, that the control bars tend to be higher than the other bars for acetate and acetate plus heat. That tells us that there was more nitrate nitrogen leaving those bioreactor modules that were just corn cobs and wood chips compared to the others that had the supplemental carbon and heat. Our constructed wetland research that we're depicting here shows our constructed wetland site. It's about 10 acres in size. Each one of the wetland cells, there are 6 of them here, we're about a ½ an acre in size. We have a pair that are on the left side that are surface flow wetlands. The middle here pair are vertical flow wetlands, and the ones on the right are our horizontal flow wetlands. And our illustration here in the upper right corner shows the deep permanent pool that we have here in the surface flow wetlands. And as that fills, we go to a larger pool that has some shallower water up at this end. And then as the water rises, it comes up again and then is allowed to flow out. The vertical flow system has narrow spaced shallow tile underneath it. So water is forced to go through and be treated by the soil and the vegetation that is there. And then our horizontal flow system is 18 inches deep and composed of a soil cap and then 2 different sizes of rock material, which allow biofilms. So the bacteria and the organisms live on those rocks and then do their work as water flows over those rocks. Now we have a treatment and a control for each one of these systems. The control basically is a lower outlet level compared to the treatment. So in this situation, we're trying to achieve a higher or a longer hydraulic residence time in the treatment compared to the control system there. So here's our annual summary data between 2017 and 2019. Again, this should look somewhat similar in terms of how it's laid out. We have discharge, nitrogen load, and flow weighted concentration. Here we have, on the left side, we have our control and our treatment for each one of those systems. So the surface flow system is a treatment in the control, vertical flow, and then the horizontal flow. Statistically speaking, when we're comparing these, we're only comparing the control versus the treatment of the surface flow. We're not comparing in this slide the surface flow to the vertical flow or the surface flow to the horizontal flow. This is just comparing the treatment and the control within a constructed wetland design type. So when we look at this data, the first thing we observe is for the surface flow and the vertical flow that there are no statistically significant differences in discharge, load, or flow weighted concentration. However, for the horizontal flow system, we do see statistically significant differences for the nitrogen load. The treatment was much lower, statistically speaking, than the control. This is mainly due to a change in the hydraulic loading rate at the outlet of the system. So there was a lot more flow coming out of the control compared to the treatment system. So most of the treatment that we had in that system was really related to the volume of water that was exported from there, because there was no statistically significant difference in the flow weighted nitrogen concentration. Now, one of the other things that's really interesting and going to be important for us to look at in the future is comparing the surface flow system to the vertical flow system, and these two to the horizontal system. Because when you look at this, this data for nitrogen shows us that we have the lowest loads and the lowest flow weighted concentrations coming out of the surface flow system compared to the horizontal system, which had the highest loads and had the highest concentrations. The vertical flow was somewhere intermediate between those two. Our monthly wetland, constructed wetland nitrate load data, again, we have a similar color scheme. So 2017 is green, 2018 is dark blue, and 2019 is light blue. These are oriented in a vertical fashion. So the surface flow control is on the right, and the surface flow treatment is on the right, but below it. And we have a consistent way to show that. So again, generally what we're looking at here is we're looking at the monthly data. So if you look at the surface flow system and the, for the control and the treatment, you can see that for 2019, the nitrate load was much higher coming out of the control than it was for the treatment in that particular year, and somewhat consistent also for 2018. 2017 is almost imperceptible on these graphs, mainly in part because of the fact that the flow was out of the systems was so much lower compared to those two very, very wet years of 2018 and 2019. We see similar results for the vertical flow system in 2018 and 2019 in terms of the behavior, and also for the horizontal flow. Although the treatment in 2018, we haven't determined why this happened, but there was much more flow coming out, or load coming out of the horizontal flow treatment compared to the control that particular year. So some final thoughts here on some of the data that I presented. As I've kind of talked about here early on when we were looking at the Minnesota nutrient reduction strategy sort of practices, but there aren't really any silver bullets there. There are lots of different practices, and not one of them all by themselves is necessarily going to solve our entire nitrogen problem. Each one of the practices that I've talked about today, and some of the ones that I haven't talked about, for example, cover cropping, they all have some advantages and some disadvantages. They have some challenges, for example. So there are some trade-offs that we need to be thinking about. Individually, the strategies that I showed today have some very promising results in terms of meeting our state nutrient reduction goals, particularly under the wet conditions. We expect that under more normal conditions like we had in 2020, that we would be equally, that would show equally as promising results. The one thing I talk about too, and is a mantra of mine, is that there's no substitute for good nutrient management. Everything that we're doing in agriculture starts with good nutrient management. And so, you know, the farmers out there, not over applying fertilizer and managing the economics of their farm is going to be really solidly in that area. And then beyond that, then we need to think about, what is Mother Nature throwing at us in terms of excess water, for example, in 2018 and 2019, that really caused some of the high loads of nitrogen. That we saw coming out. One of the things that I know some of our state agencies emphasize and is really kind of emphasized, but not in a very obvious way in my presentation today, is that practices like our drainage ditch system, practices like our constructed wetlands, provide multiple ecosystem services. So they're not just a water quality benefit that you're seeing there. There are other benefits on the landscape in those systems that can be realized. The same thing could be said with cover crops as a potential strategy. It's providing multiple services out there related to water quality, soil health, habitat, that kind of thing. We need to provide some opportunities, though, for farmers to benefit from the implementation of these practices. It's very challenging without, government programs, for example, to help install some of these practices for farmers to just to go out and install these. And so in trying to think about, innovative ways, are there ways that we can look at water, carbon, and nutrient trading in order for farmers to benefit from the adoption of some of these practices? And then finally, from a research standpoint, we've done this work where we're looking at a relatively small watershed, only about 300 acres. We really need to be scaling some of this work up where we're integrating these practices from the plots in the fields to fields and watersheds. I will thank you and also acknowledge some of my other co-authors or people that work with me at the Research and Outreach Center who are really key in helping to complete this work. Thank you.